All right, so an inverse swaps the input and the output, right? The input becomes the output and the output becomes the input. All right, so so in order for a function to be invertible, the inverse has to actually be a function, right? And remember that a function has to produce one and only one output for every input. All right, so if we reverse the input and the output, and we can't find exactly one output for every input, right? If you sometimes, like we saw in example 1, where if we tried to find time as a function of the height of the ball, right, then that we can't do it. We can't express time as a function of height because sometimes we get more than what that for a given height, it sometimes occurs at more than one time. Whereas the function where we had the value of the car that depreciates over time, for every time we have one value, for every value we have one time, and so we can invert that function, right? We could express the time as a function of value if we wanted to, if we had the right tools. All right, so that's the key thing. That's what makes a function invertible, is that the inverse has to be a function. So in order for a function to be invertible, we can look at it graphically, and so let me just go back up here a little bit. So a function has an inverse if and only if no two distinct points produce the same output. Okay, so if we know the output, then we know the input. All right, that's what makes it invertible, and these are called one-to-one functions, right? So one input gives an output, one output gets an input. All right, so if we have a function, we can tell if it's invertible by looking at its graph, and there's something called the horizontal line test. So remember, we had the vertical line test to test if something was a function. Now we have the horizontal line test to test if a function is invertible. All right, so horizontal line, if we can draw a horizontal line anywhere in this graph and it only intersects the graph once, then it's invertible. Whereas in this case, there are instances where if we draw a horizontal line, it intersects twice, and so this one would not be considered invertible, this graph of y equals x squared. All right, it's not considered invertible because sometimes we have, for a given output, we have more than one input, right? So we couldn't invert it because the inverse would not be a function. All right, so you might be asking yourself, but wait, that was x squared, right? Can't we undo x squared, right? If we take a square and we take the square root of it, doesn't that undo the square function? And yes, it does, but we have to be careful because we have to restrict the domain. All right, so when we take the square root of a function, we're only getting the positive value. So if we want, so we were essentially restricting the domain to just half, right? We're splitting this x squared function down the middle, and we're just taking this part of it, this right hand part, and inverting only that. And so the square root of a number is defined to be positive. All right, so square root of 4 is always 2, not plus or minus 2, right? There's only one answer to the square root of something. All right, we'll talk more about that later too. But let's take a look at example 3. Here where we have two functions, f and g. All right, and I've given the output a letter, y equals f of x and z equals g of x. Okay, so we have this table of values. And so we are asked if f of x is invertible. All right, so remember, we're swapping the input and the outputs. So we give it a y value, right? And we want the f inverse gives us the x value corresponding to that. All right, So I'm just going to make a table of values, and then we'll see if it's a function, then then it's invertible. So the y values, the output of f, right, are 3 and 4 and 8 and 5. Okay, and then the inverse of 3 of the inverse at 3, f inverse of 3 would give us the x value, right? So the inverse would give us the corresponding x values. So this would be 0, 1, 2, and 3. Okay, we just swap the input and the output. And then we just have to test this, is that a function, right? Does every y value give one f inverse value? And it does, right? There's no cases where we'd have a y input that gives us two different f inverse values. So yes, this is invertible. So f inverse of y is a function. Function, which is what makes f invertible, right? Okay, so f of x is invertible because the inverse is a function. All right, so let's look at g of x. All right, so in this case, I called the output z instead of y, just to distinguish it. And we could create a similar table. So we're looking at g inverse of z. All right, so remember, if g is invertible, then the inverse would give us the x value, right, that corresponds to that output, right? So our inputs are z values, right, which are the g values, right? The output values of g are the input values to g inverse. So 2, 9, 7, and 9, which might make you suspicious right there, because 9 occurs twice. Corresponding x values are 0, 1, 2, and 3. So 9 can occur twice just as long as you always get the same answer, right? So here, if you put in z equals 9 into the inverse, you would get 1, and in this case, you would end up with 3. Okay, so this one is no. So g is not invertible because, as we've shown here, if we tried to create an inverse, which it's not invertible, so because it's not a function, is not a function, right? If we tried to create a table of values, right? So this g inverse is, it's not an inverse, right? Right? G is not invertible. So because this, the g inverse would not be a function. Alrighty. Well, I will meet you in the next video for the next example.